What if I told you that the most powerful building material in human history has been inside your body this entire time? Not extracted from a mine, not manufactured in a factory, not shipped across an ocean, just sitting there, quietly, every single day, waiting to be understood. Scientists recently demonstrated that ordinary sand, the kind you'd find on any beach or backyard, can be transformed into solid, load-bearing stone using a single biological compound. No cement mixer, no kiln, no industrial process. Just biology doing what biology has always done, long before we built our first city or poured our first foundation. And here's the part that should stop you cold. This process costs almost nothing. Stay with me, because what you're about to hear isn't science fiction. It isn't fringe theory. It's peer-reviewed, laboratory-tested, and it connects to something humans have been doing, unknowingly, for thousands of years. The ancient Romans built structures that have outlasted everything modern engineers have constructed. Their harbors still sit beneath the Mediterranean, harder today than the day they were poured. For centuries, scientists assumed it was some secret recipe, some lost ingredient we'd never rediscover. What if the answer was something far more personal, far more biological, and far more available than anyone expected? Here's the thing about revolutionary ideas. They rarely come from the place we're looking. We spend billions developing new materials, engineering synthetic compounds, designing complex manufacturing systems, and all the while, nature already solved this problem millions of years ago. The compound at the center of this story is urea. It's a waste product. Your body produces it constantly. Every cell in your body participates in its creation. And for most of human history, we treated it as something to discard. But what if discarding it was the biggest oversight in construction history? Think about how we build things today. Concrete, the backbone of modern civilization, requires limestone to be heated to nearly 1,450 degrees Celsius. That process alone accounts for roughly 8% of all global carbon emissions. Every sidewalk, every overpass, every foundation slab comes with an invisible environmental price tag that most people never see. And it's not just the environment. Cement is expensive, it's heavy. It requires specialized equipment to mix and pour. It needs weeks to cure properly. In remote areas, in disaster zones, in developing regions where infrastructure is desperately needed, traditional concrete is often simply not an option. The system we rely on is costly, carbon-intensive, and completely inaccessible to billions of people. There has to be a better way. And it turns out there is. It was just buried under a century of industrial thinking. The process is called microbially induced calcite precipitation, but forget that phrase because the actual concept is beautifully simple. When urea meets a specific type of soil bacteria, a chemical reaction begins. The bacteria break the urea down into ammonia and carbon dioxide. The ammonia raises the pH of the surrounding environment, making it more alkaline. In that alkaline state, calcium ions present in the soil bond with carbonate ions to form calcium carbonate, which is, at its core, the same mineral that makes up limestone, marble, and seashells. In other words, the sand particles get glued together by natural mineral crystal, not by heat, not by pressure, not by synthetic adhesive, by chemistry that has existed in the earth for hundreds of millions of years, and urea, your urea, is the trigger that starts the whole process. Here's how it actually works, step by step, because the mechanism matters. You start with loose sand or granular soil. On its own, sand has no structural integrity. Pour water on it and it shifts. Apply weight and it collapses. It's essentially tiny particles with no reason to stay together. The first element you introduce is the bacteria, specifically strains like Sporosarsina pasteurii, which are naturally found in soil and water in many environments around the world. These bacteria have a specific enzyme called urease. Urease is a biological catalyst, meaning it accelerates a chemical reaction that would otherwise take years or never happen at all in a controlled time frame. The second element is the urea solution. When the urease enzyme contacts urea, it splits it apart. This releases ammonium and carbonate ions into the surrounding liquid. The carbonate ions are the key. They're now available and reactive. The third element is calcium, usually introduced as calcium chloride, a compound that dissolves easily in water. When calcium meets those carbonate ions in the newly alkaline environment, they crystallize into calcium carbonate, calcite. That calcite deposits directly at the contact points between sand grains, cementing them together at a molecular level. Within hours to days, depending on concentration and temperature, the sand begins to harden. Within weeks, what was loose granular material becomes something you could stand on, drill into, or build with. This is not a theory. Researchers at the University of California, Davis, and teams across Europe have demonstrated compressive strengths approaching those of soft sandstone. Some formulations have achieved over 1,000 pounds per square inch of compressive strength using nothing but sand, bacteria, calcium solution, and urea. Now, how would this process actually be applied? The steps are more straightforward than you might imagine. First, you prepare your bacterial solution, a liquid culture of urease-producing bacteria, which can be grown in simple nutrient broth or sourced from natural soil samples. Second, you'd mix your cementation solution, urea dissolved in water combined with calcium chloride. These are both inexpensive, widely available compounds. Urea, in fact, is already mass-produced as agricultural fertilizer, and it's sold by the ton at prices that make cement look extravagant. Third, you'd saturate your sand, either by pouring the solution from above in repeated applications or by injecting it from below using perforated pipes. The goal is even distribution, so that crystallization occurs uniformly throughout the material. Fourth, you'd allow curing time, anywhere from 24 hours for initial hardening to several weeks for maximum structural strength. During this period, the bacteria are actively working, constantly producing calcite and filling the microscopic gaps between grains. Fifth, and this is critical, you'd test the material. Not every application will produce the same result, because soil composition, temperature, bacterial concentration, and pH all influence the outcome. A simple compressive test, even pressing the surface with a known weight, can tell you whether the process is working as expected. Now let's put this in context, because the comparison to traditional methods is where this becomes genuinely remarkable. Portland cement, the kind used in virtually all modern construction, costs between $100 and $150 per metric ton, and that's before transportation, labor, and equipment. The carbon footprint of producing 1 ton of cement is approximately 1 ton of carbon dioxide released into the atmosphere. The water consumption is enormous. The curing process is sensitive to temperature and humidity. In hot climates, freshly poured concrete can crack. In freezing conditions, it can fail entirely. Contrast that with biocementation. The primary cost is bacterial culture and calcium chloride, both of which are significantly cheaper than cement per unit volume. There is no heat required. The process actually works better in moderate temperatures, which describes most of the habitable world. The carbon footprint is near zero. In fact, because the process sequesters carbon into solid calcium carbonate, it could technically be described as carbon negative. And the material itself, biocemented sand, has been shown to be highly resistant to erosion, to water infiltration, and to biological degradation. It doesn't crack the way concrete does. It flexes slightly at a microscopic level, which makes it more resilient under certain load conditions. But let's be completely honest here, because this technology is not a replacement for reinforced concrete in a skyscraper. It's not going to hold up a suspension bridge. The compressive strength, while impressive for an organic process, doesn't yet match high-grade structural concrete. Large-scale application still faces challenges. Ensuring uniform bacterial distribution across wide areas, controlling the process in variable environmental conditions, and scaling up production of the bacterial cultures without creating new logistical problems. In saturated or permanently wet environments, the calcium carbonate can slowly dissolve over long periods. In extremely high load applications, foundations of multi-story buildings, roadways under heavy vehicle traffic, biocementation in its current form would need to be augmented or layered with other materials. This is not a magic solution. It's a powerful, underutilized tool that belongs in a specific set of applications. Desert stabilization, erosion control, emergency foundation work, low-cost housing in developing regions, remote area construction, and environmental rehabilitation projects, where the goal is stabilization rather than maximum load-bearing capacity. Within those applications, it's not just competitive, it's often superior to everything else available. What this really represents is a fundamental shift in how we think about materials. For most of human history, we've tried to dominate nature, to heat it, compress it, synthesize it, force it into forms it wouldn't naturally take. And that approach has built civilization as we know it. But it's also left us with a planet warming under the weight of industrial emissions, with communities that can't access the infrastructure they need because the industrial supply chain doesn't reach them. Biocementation doesn't ask nature to comply. It asks nature to continue doing what it's always done, just in a place and time that's useful to us. The bacteria don't care whether they're stabilizing a sand dune in the Sahara or filling the pores of a disaster relief foundation in the Philippines. They just do what bacteria do. We're finally smart enough to point them in the right direction. Picture this for a moment. You're in a remote community. No hardware store within 100 miles, no cement truck that can navigate the roads, no budget for imported materials. The ground is sandy, unstable, unable to support a permanent structure. Children are being educated in temporary shelters that flood in the rainy season. Now imagine that a local team, no engineering degree required, mixes a solution in a simple tank, applies it to the ground in 3 repeated treatments over 2 weeks, and watches the surface harden, watches it hold weight, watches it stop eroding. The cost? roughly the price of agricultural fertilizer and a bag of calcium chloride from a farm supply store. The result? A stable floor, a foundation, a platform that could support walls, a roof, a future. This isn't a distant hypothetical. Pilot projects have already demonstrated exactly this in parts of Africa and Southeast Asia. The technology works. The only thing missing is awareness. And that's why this conversation matters. Not because you're going to go home tonight and start biocementing your backyard. Though honestly, some of you might find that genuinely fascinating as an experiment. It matters because the way we solve problems is shaped by what we believe is possible. For a century, we believed that building solid structures requires industrial infrastructure. That belief has left billions of people without access to safe, permanent shelter. This research doesn't just offer a cheaper building material, it offers a different philosophy. It says that the tools for human flourishing might already exist in the natural world, that the answer to some of our most urgent infrastructure problems might not be found in a factory or a laboratory, but in the soil beneath our feet and the biology inside our own bodies. If that doesn't make you look at the world a little differently today, watch this video again tomorrow. Share it with someone who builds things, who thinks about sustainability, who believes that the best innovations are often the ones hiding in plain sight. Because the future of construction might not be made of steel and synthetic polymer. It might be made of sand, bacteria, and something your body makes every single day without even trying.